Water can be a gas, sure. Hydrogen, carbon is not a gas though. Carbon, unfortunately, is always solid. You have diamonds, you have graphite, right? Pencil lead. Oh, it's not, carbon by itself is not in the air. It's in a couple of compounds. Can you name a compound that's a gas? Oh, it's in a compound. So we actually breathe it out. Of course, we breathe it in too. So what compound is it? Hello, Via. Hello, Francisco. Hopefully you guys had a fabulous weekend, and we are just naming some gases in preparation for class. Fluorine is an excellent example of a gas. We still haven't gotten the gases that have carbon as part of the formula though. Chlorine is a gas, helium is a gas, definitely. No carbon in those. They're like carbon blank, they're two words. Iodine is, I feel like iodine's a liquid because you buy it and you put it on your sores to clean them. But I think on the periodic table, iodine is considered a solid. But I think when they put it in alcohol or something like that, and that makes it a liquid. So like when you go to the store and buy iodine, it is just a liquid. It's inside. It's dissolved in something else. Anyway, Jasmine has gotten it. Carbon dioxide. Excellent, Jasmine. That is a gas. Sulfur is generally found as a yellow solid, but it does exist also as a gas. No, you're good, Ace, because if you can smell it, then it's a gas, right? All right, so welcome. It's 2:11 now, so we are here on September 3rd. Happy Tuesday. And well, oxygen is odorless and colorless, so you cannot smell it. But like if you smell your food cooking, that's because that food, part of it has come up to be a gas and it gets into your nose. Well, Ace, they have tested that and they know. I'm not exactly sure how that gets tested, but like water is odorless and colorless and flavorless. Yep. Okay, so let me just remind you about parking it, and I will remind you about this one. Make sure you read and actually respond to communications if necessary. Very important. That's how we figure out a lot of stuff, is how you respond to it. So if it requires responses, please hit reply. Make sure you keep your behavior respectful and courteous at all times. And today we're starting a new standard. This is SPS 5. Like I said before, we kind of skip around the standards in the direction that Edgenuity wanted to put the curriculum in. So that way we get it in a couple of different orders. So this one is all about gases and molecular motion. And we've actually already done part A, and we're just working on part B. We're gonna plan and carry out some investigations to identify the relationship among temperature, pressure, volume, and density of the gases. Oh, you're already skipping ahead. Okay, I'm going to, because it says investigations and stuff, I'm gonna take you to my kitchen today. And I'm gonna do a little experiment investigation. kitchen tour. There's my ceiling. All right, so I have some ivory soap. And you all know why ivory soap floats? Here we go. I'm doing this away, just so you know, I'm away from my computer here. But there's ivory soap, and it floats in water. It is the only soap that floats nicely in water. And it's slippery. I'm gonna just show you that other soap, and this is one of my daughter's soaps, that they all sink in the water, so that this soap is shaped like a frog, or was. But yeah, that most of them sink. So why does ivory soap float? Get that out of there. It's fake. Okay, we're talking about gases today. Just get the soap off my hand. So we're talking about gases. What do you think is in the ivory soap that makes it float? Yes, Reliable has a lower density, and it may or may not be oxygen. I'm guessing that they just take air and they like whip up the soap, and then they harden it down into the bars so that it has just gas inside. So air molecules, I'm sure that's the least expensive way to do it. Okay, and so if I take a piece of ivory soap and I put it in the microwave, what am I going to change about it? Am I going to change the temperature, the pressure, the volume, or the density? Okay, so that's going to change the temperature. So what's it going to do to the temperature if I put it in there? We're going to cook some soap. So it's going to make it increase. Yeah. Okay, so it hasn't taken more than a minute today. And so when the temperature of a gas increases, what do you think that's going to do to it? So it would increase the pressure. Sure, so now it's pushing out, right? And so, well, it might make the particles of soap move. Yeah? All right, so you ready? Or you got any more guesses as to what's going to happen to the soap? It's going to definitely have more energy. Any ideas about it? You think it'll melt, foam up? Oh, change with a solid. Let's see if it melts or foams up. All right, I'm going to start. And see if I can get pretty good visual there. And so yes, the air inside the soap heated up, created additional pressure, and then of course the soap gave way, and what happened to the volume of the air? All right, I think that's pretty good. It's coming out of my microwave. It's trying to escape. All right, and of course it's come back down in volume there a little bit. But there we have our bar of soap. All right. Is it hard? Oh, that's a good question. It's warm. It's like flexible, and it just kind of comes apart. I'm sure it would float even better now. Let me get that piece off the floor. I don't know if it's like silicone. It just, I'm trying to think of something more like cotton candy-ish, but hard and brittle. Brittle cotton candy. That's what I would call it. A little more dense. Well, I don't think I would want to taste it or eat it, although it smells really good. But yeah, my kitchen and my microwave smell really good and soapy and clean. All right, so one of my goals this year is to do more demos, and so there is my demo for today. I don't succumb to any peer pressure. You should never eat soap. It's got a high pH. It's very basic, and so it can make you sick. You don't want to eat soap. Good for cleaning. We'll do that next instructional cycle, maybe the third one. All right, cool. I hear some people already giving me their answers to the question on the board. I'll be quiet so you can do a knowledge check. We're going to rewind just a little bit and see what you remember from last week. Oh, and I see some more of you guys have arrived. Hello, Gabriel. Hello, Hannah T. and Innaman. How are y'all doing today? Hello, Joseph and Permata and Merkayla and Sahir and Zuleika and Via. Welcome, welcome. Uh-oh. Uh-oh. Gear and refresh. All right, gear and refresh. All right, so I'm still missing a couple of answers. Remember, there is a red X for if you have no idea what's going on. That way I know that you are still here with me, but you're unsure about the answer. No one can see your answers, and I will never call you out on a red X unless you want me to. But that way I know that there are people who need more help. And Ace, you wanted to get on the mic and explain this one? Ariel, did you want to get on the mic?
Molecules lose energy and their relative motion decrease because when you go from a liquid to a solid, the particles slow down and they lose kinetic energy.
Okay, so they slow down, they lose energy, which means gain energy is out, right? And yes, I could hear you just fine, Ariel. Very nice explanation. Thank you. And when they, since they are losing energy, then of course they're going to move around less. Like if you're more tired, like you've lost all your energy, it's gone, your motion is definitely going to decrease, right? So we're going here with the turtle. All right, thank you so much, Ace, for that explanation and for you guys swapping your answers. You know, I just copy and paste what I find in Illuminate in that testing program, but I'll tell you the next one is not turtle. Yeah, maybe it's that turtles are awesome. Maybe I just subliminally put the right answer in turtle. I don't know, because they're so cute. All right, so here is one that is a little bit tougher. Let me go ahead and clear out the feedback. Yes, this one was a little harder. Let's see, we still have some answers coming in. No one has picked turtle. So tell me in the chat why turtle is wrong. Right, when you heat something, you're adding energy, right? And this is saying that you remove some of their energy. So that's the problem. Yeah, the particles are going to speed up, not slow down. Is there another one that mentioned that they would slow down? Yeah. Yeah, the OK sign says something about them flowing across as a liquid. Like, what is that about? So, and removing their mass. Remove their mass. You can't just take away mass. That would break the law of conservation of matter. So, yep, the OK symbol is not good. And I'm seeing that we're about split between smiley face and the loudspeaker. So let's look at the smiley face. Heating the particles cause them to react and bond with gases in the air. So, which carry the liquid ethanol particles around the room. Would they still be liquid? So that's a slight problem. Also, if we're just talking about turning from a liquid into a gas, are they going to react and bond? No. So those are the issues I see with the smiley face that tell me that that's not the right answer. And we'll look at this actually today, how the heating the particles energize them. They collide with the container more, and every now and then they go right up to the liquid surface and they'll pop right out and become a gas. So let's see. Don't see any red X's. Almost everybody's got an answer, so thank you guys. Better participation. Any questions about this one today? All right. So let me go back to my PowerPoint. And so our goals for today are to explore the behavior of gases. And the standard, if you think back, it mentioned actually at the bottom, you may not have read it, but it specifically mentioned that we do not need to be able to calculate these things. However, if you feel like you want the math that would give you a little more background, then you can go all the way through the lesson. No ACE, we have to be able to calculate half-life. So, all right, well, we're taking a break. So this time we just really want to understand the relationships. Like when the temperature goes up, the pressure goes up. So that's directly related. And if the temperature goes down, the volume's going to come back down. Because when I took out the plate out of the microwave, remember everything collapsed? That's because it got cooler, and so the volume got smaller and it all collapsed. So anyway, that's what we need to know. We're going to skip 9 through 12. And so we're going to come back about 15 minutes before, because I also have a simulator. I want to show you some of these things with the actual particles rather than ivory soap, which was cool. But anyway, so I'll bring you back with about 15 minutes left. So going through the lessons, what questions did you come across? Well, if you're in Metro Atlanta, it's probably not going to rain for a long time. My 10-day forecast didn't have any rain in it. All right, so I'm not gathering that there's questions about the lesson. So I'm going to move on to our gas law simulator, and I will put this in the chat in just a second. Actually, I can get it now. If you guys are going to play with the simulation on your own, then give me a green check so I don't expect you to be, you know, answering my questions. But you can still listen and adjust your simulation to match up with my questions. All right, so we've got a temperature here of 325 K. Those are Kelvin temperatures. And Kelvin is basically Celsius plus 273. So this is kind of like maybe the boiling point of water, somewhere in there. So I'm going to just make the volume a little bit smaller so it's kind of halfway. So it's easier to see if the volume is going to increase or decrease. So first thing, I'm going to heat this up. What's going to happen to the volume? Is it going to increase, decrease, or stay the same? All right, who else is playing here? Did I not hit enter on that? I'm sorry, I thought for sure I hit enter to share that link out, and I didn't. But it's there now. So Reliable's saying that if I heat this up, it will increase the volume. Does this sound familiar, like something we did? Is my mic on? Oh my goodness. Yeah, my mic is on. Anyway, so anyone want to agree or disagree with Aiden that as I heat this up, that the volume will increase? All right, Michaela's going to agree. Let's see. Does this sound familiar, like something we did earlier today? What did we do that we heated up a gas and it made the volume expand? Yes, the ivory soap in the microwave. This is exactly what happened. All right, and if I cool it down, right, what's going to happen to the volume? If I cool it down, I think we already talked about this, that the volume will go back down. So those are directly related. Volume goes up, temperature goes up, volume goes down, temperature goes down. They go the same direction, directly related. Now I'm going to lock up the volume so it's going to stay. Might as well make a nice big volume so you have lots to look at. And now let's heat it up and see what happens to the pressure. By the way, right now you are at approximately 1 atmosphere of pressure because you have 1 of Earth's atmospheres pushing down on you. Zuleika, if you were a gas, it would, but you're solid, so. Very cool, very cool. All right, so if I heat this up, what's going to happen to the pressure? I heat this up, what is going to happen to the pressure? All right, Hannah's going with increase. Who would like to agree or disagree with Hannah that if we heat this up, the pressure is going to go up too? All right, and let's see. And watch the molecules too, because the temperature is their average kinetic energy. So as you heat this up, You can see that they are moving faster and faster. And look at that, the pressure did go up. And so how are those related if they're both going up together? And if I cool it, are they directly related or inversely related? They both go up together and they both go down together. Yeah, that's a direct relationship. Up together, down together. And look at that, I'm at 10 Kelvin. That's like barely moving. Do you think these would actually still be a gas? I don't know of anything that's a gas at 10 K. But anyway, that's our simulation. Let me put it back to normal. All right, something like that. Okay, I'm going to unlock our volume, and let's see how volume will affect the pressure. So if I decrease the volume, what's going to happen to the pressure? If I decrease the volume, what's going to happen to the pressure? All right. Zuleika's going with increase. Hannah's going with stay the same. V is going with increase, pressure goes up. Okay, so I like to use my hands to kind of visualize this, and when you're taking your test, you can do this too. So my volume is going to go down. Are the particles going to hit the sides more often or less often or the same often? Let's see. And you can see that they hit the sides more often, and the rate at which they're running into the side walls, that is your pressure. That's by definition, it's kind of what it is. So it's how often the particles are hitting the side. It's the amount of force that is being exerted on the walls there. All right, and then, so the volume went down and the pressure went up. So now they're going the opposite way. This is called an inverse relationship. So if I increase the volume, that pressure will drop right back down. That's a good question. I believe that's Boyle's law. So it's hard for me to remember sometimes which goes with which. We've got Boyle's, Charles, I believe, is volume and temperature, and then Gay-Lussac's is the pressure and temperature. All those scientists' names. Okay, so what is going to happen to the pressure if I put some more gas in there? We haven't used this yet. Hello, Ava. How are you doing today? So I'm going to put in some more gas. What do you think is going to happen to the pressure? I'm doing great. Thank you. Yeah, let's see. I put some more gas in there, and look, the pressure goes up. Pressure goes up. I can even add a different gas. Put a little bit of that in there. It doesn't matter what gas you put in there. Every gas particle acts the same as another one. So the pressure goes up. What can we do? Let's see. How high can we make the pressure go? What can we do to make that pressure as high as possible? Decrease the volume. What else can we do? Add more gas. Let me add as much as I can. Oh, I got my particle limit and then heat it up. Look at that. Ooh, 108.3 atmospheres. Good job, guys. You maxed out the simulation. Well, yeah, you're right. We did. Well, we decreased the volume though. Yeah, volume's inversely related to pressure. So that goes down. All right, I'm going to reset this for my next class and go back to my presentation because I have one question about Boyle's law. All right, as you breathe in, right, the volume of your lungs goes up. What happens to the pressure and how does that help you breathe? Clear, clear, there we go. Oh, Ava, the emojis are right down here. So pick your emoji of choice that goes with your answer of choice. No, it's okay. No worries. I am so happy that you came in and you're participating, that it's okay. Annotations. All right. Due to our time constraints here, I'd like to go ahead and start chatting about this one. And I did see that someone mentioned that the pressure would go down if you increase the volume. That is correct. We just learned about that. The pressure is going to go down. So that is going to eliminate this one, that it remains the same. The other ones, oh, and this first one, smiley face is out because it says the pressure goes up. So when you breathe in and the volume of your lungs increases, is that going to push air out of your lungs or is that give air flowing into your lungs? And it looks like, yeah, you guys are going with air is flowing into your lungs. So if you're ever stuck between two questions or two answers, go ahead and look back at the question because the answer, it might help you to pick between those two if you look back at the question. Because it did say breathe in, and when you breathe in, there's no air getting pushed out of your lungs, right? The air is flowing in. So sometimes going back to the question can really help you with one that you might be stuck on. And that brings us to my information, and this is 7th period. So yes, I will see you all tomorrow for our block where we will look at some more changing states and their energy, and it'll all tie this and no, 7th period. Did I say grade? I'll go back. Oh goodness. Sorry about the 7th grade. I did not mean that. 7th period. My apologies. I will see you guys tomorrow for block, and you guys have a great afternoon.